So, I will briefly go over what we did yesterday, the last few part. Okay, we will recall what we did. So, so we were doing the formal theory of formal power series. Right. So, we had seen some applications of generating functions, right. So, we tried to solve some recurrences and in fact come up with a generating function and give a recurrence also, right. We did that for the Bell numbers. So, we were trying to understand what is the formal background, that is the tools and techniques that are going behind all these manipulations that we were doing, right. So, that is what we were trying to do yesterday. So, let us recall the setup. So, I'll use this notation for a sequence, right. So, this is a sequence of numbers and we will associate a formal power series with this sequence, right, which is some kind of it is a generalization of a polynomial, right. And this association we will write it as f is associated with this sequence, okay, and we will write O for f is the ordinary power series corresponding to this sequence, okay. Similarly, we can say that if so if we have defined f of x as, so instead of the ordinary power series, if we do the exponential power series, right. So, we can choose our closed line, then we will say f is the exponential power series associated with the sequence, okay. And what we wanted to do was, so what we had seen was that at least this, the set of all power series whose coefficients come from a ring, right, let us say ordinary power series with coefficients in some ring it is a nice commutative ring, so on, is itself a ring and we denote it by, so if we did single brackets, that is a ring of polynomials, and we do double brackets to say this is a ring of power series. So, it is not hard to see that power series are closed under addition and multiplication. And addition, subtraction and multiplication and all the laws of distributivity, associativity, all that holds. Okay. So, this is the setup where we are working in, fine, right. So, and what we are trying to do are, we are trying to formalize these rules of manipulation, right. And in fact, we had defined also f prime was just the standard way. We will do it in two parts. The rules of manipulation for the ordinary power series, that is what we saw yesterday. So, we will go over them and we will also deduce today the rules for the exponential power series, right. So, what is the setup? So, f is the ordinary power series associated with the sequence. Then what is the power series, the ordinary power series associated with the sequence a n plus 1? Right. Right. So, what do we mean by a n plus 1 would be a 1, so a 0 x, not a 0 x, A1x, sorry. Right, this is the series. A1 plus A2x plus, right. So, the power of x is 1 behind the power of the index of the coefficient, right. So, if we know that f is the ordinary power series with this coefficients, what is the series associated with this, right. So, f minus a naught divided by x. So, the series ordinary power series associated with this sequence is f minus a naught by x, and we can generalize this. If you shift by some constant k, then this will be f minus, you subtract all the things up till k and divide by x raised to k. Right. So, you just remove the first k minus 1 terms from the right side here, right, move it to the left, divide by the appropriate power of x, and this is the series associated with this sequence, right. What about a n minus 1, since we need this? So, instead of shifting forward, we have shifted back. X into f, right. We will assume a minus 1, all the negative coefficients are 0. So, a n minus 1 is this sequence is what, right. It is so at 0 it is minus 1 is does not matter, at n is equal to 1 we will get. So, the power of x is always 1 ahead of the index. So, this is x times f. Okay. Is this fine? Do we follow this? Right. The next was, so what is the sequence associated with n times n? What is the series associated with n times n? Right. So, it is almost the derivative except the power of x is off. So, x times the derivative into f. Yeah. So, we saw this x times. So, this is the derivative operator, and we generalize this to say that if you have any polynomial of n, then it is just the same, just plug in this operator and apply it to f. So, let me just erase this. So, I want to have more space here. And the last was, if f is associated with a n, the ordinary power series associated with the a n g is the ordinary power series associated with the sequence b n, then f g is the ordinary power series associated with the sequence whose coefficients are the convolution of a and b. Right. That is just the product rule applied to the series. Right. The coefficient of n x raised to n in this product is exactly this term. And we saw that this is useful if you want to do additions. Right. So, if you do f times 1 minus x, 1 upon 1 minus x, what would this be? This would be summing up. So, this will be the power series which sums up the coefficients of f, right. So, are these rules clear to us? Any questions? Okay. Now, let us deduce the same rules when we are working with the exponential power series. This, which one? This? Yeah. If R is commutative, this one. So, now let us do, let's add some space. So, let us say now f is the exponential power series of the same sequence. Right. So, there is a slight twist now, we have these factorials sitting here. Okay. So, same. So, what is the exponential power series for a n plus 1? Right. So, let us write down this. So, what is this? This is now it's like this, except you have the factorials, right? Right. So, this the exponential series is this. What is the relation between this and f? F is now this. No? Right. Let us write down f. F is a naught plus a1x by 1 factorial. So, what would our guess be? No, there are the factorials have all changed. Yeah, the derivative. It's a derivative, right? It's much cleaner now. Right? You just differentiate this so that the powers of x come down, they cancel 1 from the denominator. So, what is it for a n plus 2? Second derivative. Okay. So, well, we can apply this rule. So, like we did yesterday for in this setting, we can, let us consider again the Fibonacci sequence, but this time we consider the exponential series for the Fibonacci sequence. Right? I mean, why do we have to only consider ordinary power series? We can in fact consider the exponential power series. Now, the recurrence right. So, this same recurrence here we had when we did this, we have these manipulations, but if we work in the exponential power series world, this would imply from these two rules, the second derivative of f is equal to the first derivative plus f. So, how do we get this, right? If just I mean do the same, multiply by x raised to n by n factorial, sum it up, but these rules say that, well, this sequence of this and sequence of this are the derivatives. So, the second derivative is the sum of the first derivative and the function itself. Right. In some sense, it is much cleaner with what we did here. Now, but how do we solve for f? Right. It is all valid, but the challenge has shifted to, okay, how do you solve for f now? Sorry? right. So, this is a differential equation, we want to solve for a differential equation, right. So, how do we solve a differential equation? You make a guess, right, any differential the standard differential equation, if you say f prime is equal to s, f, right, has the solution constant time exponential, right. So, whenever you have a differential equation, you make a guess, right, the guess is f is exponential of some alpha times x, okay. That is our guess. If we figure out alpha, we will figure out, alpha has to satisfy some constraints. So, what are the constraints? The second derivative of that will be alpha square e to power alpha x, first derivative is alpha e to power alpha x, and f is e to power alpha x, right. So, alpha has to satisfy the equation, right. So, you can cancel this, right. So, what are the choices for alpha? Right. So, alpha is exactly the golden ratio and its conjugate, right. So, what this says is, okay, alpha can be either, right, as long as alpha is one of these two, it is fine. In fact, alpha can be a linear combination of these two and it is still fine. I mean, not a linear combination of these two. So, so you can say f is a linear combination. So, f is so right, even this will be satisfying the same equation, right, because this satisfies the same equation, this satisfies the same equation. So, their linear combination also satisfies the same equation, right. So, we can do C, D and D. So, we just have to figure out what is C and D, that will give us the answer. Okay, so, if you do the same thing, you substitute and you figure out. So, what you get is C is equal to minus D, C plus D is 0, and C is 1 upon square root 5, right. So, the solution f is 1 upon square root 5 e to power phi plus x minus e to power phi minus x. Okay. Does this match with what we had yesterday? We had the nth coefficient was phi plus raised to n. So, if you now equate the coefficients of x raised to n, what will you get? If n by n factorial is 1 by square root 5 n factorial, the coefficient of x raised to n in this phi plus raised to n minus phi minus raised to n, right. So, the n factorials cancel, we have the same formula for the Fibonacci number. Okay. So, you can work with either series. In some cases, it is easier to work in this setting, in some cases it is more natural to work in this setting, but you can work with either. Okay. Is this fine? Do we follow this? Just substitute f of 0 is what, right. So, you can do that. Do your boundary conditions, put your boundary conditions and okay. So, so you can generalize this. If you want to do k steps for any constant k, then this is just differentiated k times. I see. How does this rule generalize? Oh, what is the exponential power series with these coefficients? Right. So, what will happen in this case, right? Let us do n times a n again. So, the observation is an exponential power series is also an ordinary power series, right, except with the coefficient a n by n factorial, right. This is also an ordinary power series, except the coefficient is this, right. So, if you are differentiating this, it will still be the same n times a n x raised to n minus 1 multiplied by x, you will get n times a n x raised to n by n factorial, right. So, the same rule that is here will apply there, the same calculation, right. You differentiate it once, you will get n times a n x raised to n minus 1, you multiply it by x, you recover the power. So, it will be the same thing. Yes, I mean the same manipulation works here. Sorry. Yeah. And the last is the convolution. So, f is exponential power series for a n, g is exponential power series for b n. So, in this case we know what f g is, but we have to figure out what is it the coefficients corresponding to this. Okay, so let us do that. When we multiply these two, so it is not as if multiplying exponential power series has a different rule, right, it is the same rule. Since, so if you multiply two exponential power series f g, the coefficient is of x raised to n is what in right, it is summation of a k by k factorial b of n minus k by n minus k factor. I mean just by the product root, right. Treat this as the coefficient a n by n factorial. So, you will get a k by k factorial convoluted b n minus k by n minus k factorial, but that is the coefficient of x raised to n. In the exponential power series, we are not interested in the coefficient of x raised to n, we are interested in x raised to n by n factorial, right. So, we have to so if you multiply and divide it by n factorial, what will you get? So, the coefficient of x raised to n by n factorial is, right. So, you multiply by n factorial, you will get n choose k. Okay. So, this is exponential power series with this convolution. Is this fine? Do we have any questions regarding this? That this is the exponential generating series for this sequence. and this is the clue. This last rule is the clue where you want to use this ordinary power series and where you want to use exponential power series, right. If your recurrence has binomial terms, you should try to think of exponential power series. If your recurrence is a plain recurrence, something like this, then you should think of the ordinary power series. Okay, so as a warm up, maybe you can try to do. So, what is the sequence? What is the exponential power series for the sequence square? Okay, I'm just making it up. So, you have to apply these rules from some starting with two sequences and figure out what is the exponential power series for this sequence. Okay. So, but let us do a more real world application. Okay. So, we will try to come up with two numbers which are there in combinatorics and see how these two apply. Okay. Okay, let us try to do count the number of balanced parentheses. Right. So, when we are doing programming, right, we have left parenthesis has to be matched with the right parenthesis, otherwise we have a syntactical error, right. So, if you have n pairs of such parentheses, in how many ways can you have a, let us say, an authentic balanced string of length 2n? No, sorry? Yeah, Catalan number, that is right. So, what is the setup clear? What is the, so let Cn be the number of balanced parentheses with of length 2n, right. So, of length 2n means n left parentheses and n right parentheses, right. So, what is balanced? When you scan go from left to right, the number of what left parentheses do not exceed the number of right parentheses. Is that correct? Right. The number of opening parentheses is never more than the number of closed parentheses. Or is it the other way around? Other way around. The number of open parentheses is less than the number of closing parentheses. Yeah. Okay, let us do for n is equal to 1, there is only one valid string, right, one open, one closed. Okay, n is the number of pairs of parentheses, the length of the string is 2n. Let us be careful on this. Okay. So, the length of the string is always even, half of them are left, half of them are right. Okay, and they have to be balanced in this, in the programming sense. Okay. N is equal to 2. So, n is equal to 1. So, we are saying C1 is just 1. N is equal to 2. 2, right, either like this or like this, right, only two possibilities. n is equal to 3. Five, okay. What? Let's say one is this, one is this, the other way around. They're all together. Anything else?
2 in 1.
2 in 1 meaning?
Oh, all open. One set, one set.
Ah. Anything else? Is this fine? C3 is 5? Yeah. Okay. Okay, so this is the sequence that we want to understand. Right? Right, so this is a very famous sequence. It has many different interpretations. There is a whole website maybe where there are maybe 50 different ways to interpret the same sequence. Okay. So this is called Catalan number, named after a mathematician, Italian mathematician Catalan. So how do we use this this framework of generating functions to come up with a closed form expression for the Catalan number? Okay. So again we try to come up with a recurrence for the number. Okay. So let us define f and k. Okay, so if you look at any such balanced parenthesis, there is a first part of the string where it is it is balanced for the first time. Right? There is a part of the string when you go from left to right where it is balanced for the first time. Right? For example, in this case, it's already balanced here. This part is already balanced. Right? In this case, this part is balanced. Nothing smaller is balanced. Right? In this case, this is balanced. In this case, this is the whole thing is the smallest that is balanced. And is this the same here? Right? The whole thing is the least that is balanced. Right. So let's call this a name. Okay, so let's call that let's say the minimal balanced index. So the minimum balanced index is k if the first two case parentheses form a balanced string, right? And nothing smaller is balanced. Right? Nothing smaller means you cannot stop before that. Okay. So does every string has a unique minimal index? Right. Every string has a unique minimal index, right? You can't have two indices. Either one of them is the smaller and that is the smallest index, right? So this index is unique for every string of length n, of length 2n, right? So what we will try to do is we will try to count f and k, which is number of balanced, let's say legal strings, legal strings. with minimal index. Okay. Right, and since this is unique, K is unique, the minimal index is unique, Cn is just the sum of all these numbers. Yeah, so K0 is 0. Let's so whatever doesn't make sense is 0. Right, is this fine? So it's similar to what we did for the Stirling numbers or the binomial thing, right? N choose K or N Stirling, N curly K, we start with that. The Bell number was the sum of that, or the total number of sets is the sum of that. So we are doing something similar. It's the same idea, right? You start with something smaller, more concrete. The number that you are interested in is the sum of all these smaller quantities, and from these smaller quantities, hopefully, you will get a recurrence for the total sum, right. So, now can we get a recurrence for Fnk for this number? So, how can you get a string where the first 2k parentheses are balanced, that is the smallest balanced parenthesis in the starting, right. So, what can you say about the remaining n minus 2k parentheses, the remaining part of the string, that is also balanced, right. That is how many of that can be there, f of n minus k, right. So, there is something in the starting we have to count, okay, how many for k is equal to 1, how many can we have like this with k is equal to 1, the rest n minus k are balanced themselves, they need not be minimal, they have to be only balanced, right. The remaining part of the string is balanced. How many choices are there for that? Right, f of n minus k, right. And how will the first 2k strings look like, so that they are minimal? Right. If you look at all the minimal strings, the first 2k strings, they have a certain pattern to them. They are balanced, but in a very strong sense, right. At the first there is always a starting parenthesis, and the ending one is going to match this one only. The opening parenthesis cannot be matched until you hit the last one, right. So, you will have a string of length 2k, this parenthesis will be closed only by the last parenthesis. If there was something closing it earlier, then this k index is not right, this is not the least index. If this parenthesis was matched somewhere before, then the minimal index is that, right. So, the k is minimal because the opening parenthesis is matched exactly by the last parenthesis, and inside you can put anything, right. So, how many choices are there inside? Yeah, k f of k minus 1, right. You can put any balanced string of length 2k minus 2, put an opening parenthesis, closing parenthesis, that will give you a minimal string of length 2k, which is primitive. Let us call such a string primitive, right. So, do we understand this? Right. So, how can you form a string of where the minimal index is k? The first 2k have to form a string like this, which is a valid string of length k minus 1, of length 2k minus 2, and the rest is fn minus k, right. This is just balanced. This is balanced inside, but outside there is just this one pair of parentheses. Is this fine? No, fk minus, oh sorry. Oh yeah, there is a, yeah, sorry, there is a c. So c of k minus 1, c of n minus k. You're right. Yeah, so yeah, sorry. So this is just a stepping stone. So f and k is all balanced strings of length k minus 1. So that's a Catalan number k minus 1. This is Catalan number n minus k. Right. So and this is what we have. This is our recurrence. Okay, so we have a recurrence for the Catalan number. Now, which of the two power series should we use? No, not exponential. There is no binomial term. Right? It's the ordinary power series. Right? This, what is this saying? That is, right? The nth term is, it looks like this. Somehow it involves its own sequence, right? So now we have to express this in terms of the ordinary power series for the Catalan sequence. Right. So let C of x be the ordinary power series for the Catalan sequence. Now we this recurrence, this, so this recurrence will give us a relation on C. Okay. So what does this mean? Okay. So this is saying, how do we get this? This is the product of two series, right? When you multiply two series, so you have to keep this in mind, you are multiplying two series, that is the coefficient. So what series corresponds to this coefficient sequence, Ck minus 1? Yeah, Cn minus 1. What series? If C is this series corresponds to Cn, what is the series corresponding to Cn minus 1? Xcn, right? So here I'll multiply it by x raised to n and sum for n greater than or equal to 1. Okay. So this is saying xcn multiplied with xc multiplied with c, this is the right hand side, is equal to, well, c minus 1. Minus 1 because we are going, the sum is from n greater than or equal to 1. Okay, so what am I doing? So we are taking this recurrence multiplied by x raised to n, but the sum is only going starting from n greater than or equal to 1 because there is a k minus 1. Yeah, I can't start with 1 here. I can't start with 0 here, sorry. Okay. So this summation of n greater than or equal to 1 of Cn x raised to n is c minus 1. And the right hand side is xc times c. Right, where c, I am using c for this series itself. Okay. Now this is interesting. Now what do we have? We have xc square is minus c plus 1 is equal to 0. So we have a quadratic equation with unknowns. Okay. and what we will do is, okay, we will just treat it like any other quadratic equation. We will say C is then what? C is 1 plus minus so v square 4 what is it? 4x, yeah. Four AC is 4x upon 2a, right? 2x. Okay. So this series, now there are two options for this series. It's 1 plus minus whatever this is. Okay. Now there is something hidden here. What do I mean by square root of 1 minus 4x? Right, it is that series whose square is 1 minus 4x, right. F square is 1 minus 4x, right. How do you find such an F? Right. Again you go back, you look at the rules of convolution, right. What is this saying? These are the coefficients. This constant coefficient is 1, so you can start with that. The constant coefficient here is 1. You can now build up this series. You can solve for the coefficients of f, right. So this will give summation of a k a n minus k. Right, it's either 1 minus 4 or 0. Right, so you can solve like this, okay, or you can apply the binomial, whatever the binomial, the way we take normal powers and do 1 minus 4x instead of n do half. Okay, so just do the standard binomial expansion. It's an infinite expansion, but instead of n, you just do substitute half. Right. So, n choose k, do not write as factorials, but write as n minus k into n minus k minus 1, so on, so on, so on. Okay. Okay. So, let us assume we can do that. So, but still there is an option C. Which of these two is C of x? Right, there is a plus option, there is a minus option, right. Which of these will fit our choice, right. So, what do? We try to find out what is C0, right. We know C of 0 is 1. Okay. If you do minus here, what will you get?
0 by
Huh?
0.
So, you have to find the limit of this as x tends to 0. So, if you do plus here, you are in trouble, right, because plus will here, this 0 in the denominator will blow it up to infinity, right. But if you do choose minus here, then this 1 and 1 cancels off, you will get a power of x outside, that x will cancel off. Okay. Or do take limit x tends to 0, figure out what is C of 0. If C of 0 is it's infinite in one case, it's 1 in the other case. So, the other case applies minus here. Okay. So, this is the generating function for the Catalan sequence. Do we is it okay so far? We still have not got we have got a recurrence, we have got the generating function, then but what is C of n still? We have not got a closed form expression for the number itself. So, what do? If you again open it up, try to find the coefficient of x raised to n plus 1 on the right hand side, that is C of n, and if you do this binomial thing, then then C of n will be this number. Okay. So it's basically saying find the coefficient of x raised to n plus 1 in this series. Why n plus 1? Because there is a x sitting here in the denominator. So now if you know the formula, then you can argue directly what should be the number of balanced parentheses, right? And you can maybe do this directly. And did anyone try the third identity from yesterday? Yeah? Did you try to prove it using generating functions? That so we had k from 0 to n. Yeah, it's a product of two series. Which two series? Right, this was what we wanted. Okay, what is this now? Now if you look at it, this is just the convolution of the Catalan series with itself. Right? If you take 2n choose n, this is 2n minus k choose n minus k. If you just take the convolution of the series with itself, the coefficient of x raised to n is what you are looking for. If you apply it to this, right, then you will get it. So this is 1 minus this times itself. So what you will get is the coefficient of x raised to n will be some power of 4, that is at 4 raised to n. Okay. So you can work it out directly by, if you know this series, the answer is in that product. Okay. Or you could do it by hand, multiply by x raised to n, apply these rules and get the same answer. Okay. So that was an illustration of this rule. Let me do an illustration of, let's do an illustration of this rule. Any questions before we move to the next step? This is fine? Sorry? This, yeah? Okay. Yeah, I mean the power series is the Taylor series after all. Right, but it's what is half choose, and if you understand this now, if you define this the way half choose k, let's say, right, just write the formula of n choose k but without the factorials. That is the coefficient. Okay. So let's do derangements. Right. So what is a derangement? Even over n, let's say. Right. Has anyone seen this derangement? We are a lot of deranged nowadays. Sorry? Yeah. So what is none? What is permutation, right? So it's a permutation of n elements, right? So that no element is mapped to itself, right? So, right, if if it was the case, if I is equal to pi of I, then we say this I is a fixed point. If for example 1, 2, 3, if you just rotate it in 2, 3, 1, right, where 1 goes to 2, 2 goes to 3, 3 goes to 1, that is a derangement, right. So, if you randomly pick a permutation, what is the probability that you hit a derangement? These are like some favorite interview questions that we have. Huh? Right. So, let us say dn is the number of derangements. So, dn by n factorial, that is a very nice answer which means nothing, right. So, we define dn as the number of derangements sir, and divided by n factorial, nice. So, but yeah, it's we will see that what is this, it is close to 1 by e as n blows up. So, lot of derangements, right. In the set of all permutations, there are many of them, right, a constant fraction which have no fixed point. So, derangement is what? A permutation with no fixed point. Right, and there are various ways to find this number. What we will see is one of the ways to do this. Okay, let us do it again. So, let us again we define, let us say P and K. So, number of permutations with exactly K fixed points. Right, if you have this, so there is some benefit of definitions that it helps our life. So, what is n factorial then? The set of all permutations, every permutation has a certain number of fixed points, right. What is Pn 0? Right, with no fixed points is what we are interested in, right. Right. So, every permutation has a certain number of fixed points, it is unique, right. So, n factorial, if you sum these numbers, the total number of permutations is the sum of all these numbers, because the partition is the permutations are partitioned uniquely with respect to the number of fixed points, right. Sorry? By the number of fixed points. Right? Does it have 0, 1, 2 all the way up to n, right? And okay, what is P and K? So again, if you can come up with a formula for P and K in terms of the derangements, it will help us. How can we form a permutation which has exactly K fixed points? Yeah, and choose, yeah, so why is that? So pick any K elements as your fixed points, the remaining n minus K, they have to be deranged, there cannot be any fixed points in them, right. So we have that, okay, this is the, now which power series should we associate with the derangements? right? It looks like this, even though we do not have a recurrence here explicitly. We are not saying dn is equal to this. In fact, dn is sitting right here. For k is equal to 0, dn is here. It is not a recurrence per se. Right? It's just it also, but it still says dn is n factorial minus the other derangements, right? I mean, this is, it does express dn as n factorial minus. So, in that sense, okay, maybe in this form if we say it is a recurrence, right. So, let us look at this now and we define, let's see. So, d of x is the exponential generating function for the derangements. So, how can we write this? So, we want to express from this, we want to derive a relation on this function itself. No, maybe a bit hard. Let us multiply and divide by, the problem is this n factorial. So, let us multiply and divide by n factorial and take a sum. Right. So, what is the right hand side? Right hand side is an exponential generating function whose coefficients are of this form. How do we get coefficients of this form? From D? How can we get such a coefficient? Right? One is D, the other is 1, right? One is dn minus k, the other ak is 1 here on, right? You can say this is times 1, right? So, we are multiplying d, the series, the exponential series d with which series to get this coefficient? The exponential series, right? What is the exponential? I mean, what is the series associated with the sequence 1? Right? What is the exponential series? All whose coefficients are 1? E power x, right? Just like here, the series, the ordinary series associated with all coefficients 1 is the geometric series, right? So, these two play the fundamental role here. So, what we get is, from the last rule of convolution, we get that this is the series d times E of x. This is just, what is this? This is left hand side, there is no exponential series, it is just the standard ordinary power series. So, what we get is d of x is e to the power minus x times 1 minus x. Is this step clear? Right, this is the heart of what happens. So, how do we get, so this is an exponential series, right? An exponential series whose coefficients look like this, right? What does it look like? N choose k, dn minus k, and another series whose coefficients are 1, right? What is that series whose coefficients are 1? Right, the exponential series has coefficients 1. So, this series is obtained by multiplying d with the exponential series. The left hand side is the ordinary summation, it is not an exponential series, the left hand side is an ordinary summation. So, we get the ordinary power series. So, we get the exponential power series for the derangements is e to the power minus x divided by 1 minus x. Now, we apply the convolution rule on this side, right, because dividing by 1 minus x means sum up all your terms up till n. So, dn is what? So, this is if I just write the exponential power series 1 by 1 factorial. Right. So, if you when we multiply this series, we divide this by 1 minus x, we add up all the coefficients all the way up till n. So, dn is 1 minus 1 by 1 factorial plus dn by n factorial is this. Okay. So, this is the exact formula for the left hand side, the coefficient is dn by n factorial. We have to be careful here. Left hand side, the coefficient of x raised to n is dn by n factorial. Right hand side is this sum. Okay. So, this ratio dn by n factorial is this sum. Now, if you take n tends to infinity, this is 1 by e. That is what we had written there. Okay. But if you look at this formula, you can use a different approach to compute dn, right. You can do principle of inclusion exclusion, that is what is happening here, right. So, if you multiply by n factorial, how many permutations have one fixed point, how many permutations have two fixed points, at least one fixed point, at least two fixed points, at least three, at least four, do the inclusion exclusion, and that is what that is. In fact, it looks like we are going down substantially because the first two terms cancels off, but it makes up later. Okay. Yeah. So, yeah, any questions? So, this is just an illustration of how you work with these generating functions. Now, this is not the end of the story. You can think up of any different series that you have seen of. Okay, you can do hypergeometric series, hyperbolic cosines, hyperbolic sines, and just as we did for exponential, you can start working with those series, and they will have a corresponding set of rules. So, depending upon the nature of your sequence, the recurrences, that is where the art comes from. Which series will you choose from, right? Will you choose the ordinary power series, the exponential power series, or some other power series? Okay. So, it may be the case that for some numbers, some other series plays a more appropriate role. So, and if you come up with a sequence, what do? If you first you come face to face with the sequence of numbers, what should you do? You go to the online encyclopedia of integer sequences. Okay. So, online encyclopedia of integer sequences. There is a website maintained by for a long time by some mathematicians, and you can search for your sequence. So, you write the first few numbers in your sequence, and the encyclopedia will tell you all the sequences which match the starting few numbers. And not only that, it will tell you all the possible generating functions that they know of, and they will tell you all the recurrences that we know of. So, whenever you end up with a sequence that you are not familiar with, you want to understand it, you can always look it up. So, this is the correct Wikipedia to look up for integer sequences. Okay. And you can find out all these properties there, right. But for some sequences, we may not have such a generating function, for instance, for primes, right. We may not have such a thing. Okay. So, I will stop today here. So, what we will next do is, so far we have only looked at the algebraic aspect of the series, okay. We have only done these algebraic manipulations here, but now you can ask, well, if you do have the series, right, there must be more to it. Why not use the, so we have all these, yes, so the derangement is this. Well, this must, now this series has some geometric properties also, right. There is a radius of convergence of that series and so on. So, does that have any bearing on your sequence? So, we will try to look at that area also. Just briefly we will look at it, the analytical aspects of generating functions. Okay. So far we have avoided doing that. We have just worked at it as formally in this setting. We have never substituted any value for x, as we had said. Right now, if you start substituting values of x there, we have to worry about properties of convergence and so on. Okay. So, okay, you have that the Catalan number is 2 n choose n roughly, but how large is 2 n choose n? What is the asymptotics of 2 n choose n? Is it more than 4 power n, less than 4 power n? No. So, what is, you want to get the precise asymptotics, precise meaning up till even the leading constant. So, we can use the fact that the Catalan sequence has a certain generating function. The properties of that generating function, the analytic properties of the generating function govern the asymptotic behavior of the sequence, and much more. So, we will do this and we will do unimodality of sequences. Okay. So, we will meet tomorrow. Any questions?